there's been a suggestion that those clouds might actually be made of little diamondoid nanobots, right? And someday, if they turn out to be a reality and we can get the opportunity to explore and investigate what the content of these clouds are, we may be surprised that it is in fact someone else's nanobots boldly going between star systems.
Jill, it's good to see you. I think it's been 12, 13 years since we had our last conversation. A lot's happened.
I was a much younger person when we last spoke.
Well, I was going to say that we're both pretty much the same. It's the world that's gone crazy.
For sure.
You know, I was actually thinking, with all the problems in the world, the fractious relationships that we have today, that it's said that the only way to get humanity to work together is to have some hostile aliens threaten us. So I'm counting on you to supply them.
Well, I don't think we have to wait for a threat from hostile aliens. I think just working on SETI is a really good way to unify people, because when you think about what we're talking about, life beyond Earth, something that is totally different from us, it has the effect of holding up a mirror to all of us and emphasizing the fact that when compared to something else, we're all the same. And I think that's really important in this particular time where we have all of these challenges that actually don't respect national boundaries. So we need to work on these globally, and I think SETI is a cosmic perspective is a good framework for thinking about these.
How has that been happening? What has been the international elements of SETI over the last 10 years or so?
Well, the current funding for SETI comes from a philanthropist, Yuri Milner, and the team at Berkeley that he's funding is using telescopes around the world. Right now in the US and West Virginia, in Australia, and they are beginning to outfit telescopes in South Africa and in the UK and in Western Australia. And they have plans to use many other telescopes, including, eventually we hope, an international telescope called the Square Kilometer Array, which will be built in South Africa and will be the biggest thing that we've ever done. And it will be an international project, although, sadly, in 2011, the US formally dropped out of that collaboration. Yet many of our scientists are still working on the project.
What are the capabilities of the array? How will it be different from the traditional methods?
Well, it's 50 times more sensitive than any telescope that we have on the planet today. And because it's in the Kalahari Desert of South Africa, we hope that the background will remain low throughout the lifetime of this telescope. It's got a huge ability to not only find faint signals because of the large collecting area, but because it's an array that's spaced out over multiple countries, actually, we can have extremely high spatial resolution. And that's really important with a SETI search, because being able to spatially resolve, to actually know where the signal is coming from, helps us to avoid or discriminate against our own technologies, our own interference. So with a large array like this, when you try and make a radio image of the sky and see actually where the source is coming from, interference, either in orbit, satellites, or local, those signals don't correlate, so you can't make a radio image. But if it's really a signal coming from the sky, moving at sidereal rate, moving the way the stars and the move on the sky, then we can make a radio image and actually know where that signal's coming from. So,
what part of the electromagnetic spectrum will the search be focused on, or how broad can it be? Because I think that's an important part of having a broad scope, because in the past we've been very narrow in our ability to analyze different parts of the spectrum?
Well, from any particular telescope, you're going to be limited to how much frequency coverage your receivers have. The square kilometer array will give us an opportunity to observe from 1 to 10 gigahertz. But we also have other projects now on optical telescopes and on infrared telescopes. So we are trying to cover the spectrum. And we also have a challenge. We'd like to look at all the sky all the time, because signals may be transient. And you have to be looking in the right direction when that shows up, with the ability to verify and give you confidence in what you've seen. So we're also building a couple of telescopes that have huge fields of view. And in one case, if we can build out all of the different locations that we're eager to do, we will actually be looking at all the sky all the time. And in both cases, these telescopes are optical right now. We haven't got the ability to do it yet in the radio, but we're going for that.
As you look at the whole spectrum, what are the different kinds of content that would be applicable to different elements of the spectrum, whether it's radio or optical?
Right now, we're using a lot of compute resources in all of these sites and all the different frequencies. And we basically are asking the computer if there are any particular patterns in frequency and time that we've pre-described as being something that Mother Nature just can't produce. So in the radio, we look at frequency compression. We look for narrowband signals. And in the optical, we look for time compression. We look for bright optical pulses. And these are the categories of signals that we currently have sensitivity to. But the wonderful thing is that now that machine intelligence is getting to be so useful, we are getting to the point where we can simply train a neural network with a lot of old data. And then instead of telling the machine, go see if this pattern in frequency and time exists, we can just simply ask the machine, is there any information in that signal? Right? We don't have to pre-describe and limit our sensitivity to a particular type of signal. So this is one of the new things that's happening. And so in addition to looking all the sky all the time, we're going to build machines that are intelligent enough to tell us when there's something there that's anomalous.
The international collaborations that you're having, at what level are they? Are they governmental? Are they university? Are they entrepreneurs who are funding? How does it work?
Well, radio astronomy has historically been ground up, right? The astronomers decide what they'd like to do. They form groups within their own countries. They have access sometimes to their national funding agencies. And then we bring in more partners as it gets too expensive for any one nation. And so the Square Kilometer Array, which is the largest ongoing international collaboration in the radio part of the spectrum, that really started from the astronomers who would get together globally every 3 years at a meeting, and we started to talk about what we wanted, and then we tried to work our way through the political situation. And in the US, every 10 years, we do a decadal review of astronomy and astrophysics. And the community, rather than the bureaucrats, decide what their priorities are for the coming decade. And indeed, the projects are usually so big that it takes more than one decade. But it is really encouraging that we have the opportunity to self-select, to rank various projects across the spectrum of different research in astronomy and astrophysics, and say, yeah, you know, this instrument is going to bring so much more information. We're going to explore new regions of the cosmos that we haven't done before. And we think we should do this. So that gets a high rating.
Yeah,
and other countries have similar kinds of reviews for ESA, for example. And it's a privilege that the scientists who are actually doing the work get the ability to say, and this is what we want to do.
Over the last decade, we've obviously had a great increase in knowledge of extraterrestrial planets, where we now know that there's at least one planet for every star on average, and maybe more, and huge numbers in the so-called Goldilocks zone, where you'd have liquid water and the requirements for life. Have those affected the so-called Drake equation, which gives you some kind of predictability of what the likelihood, either in our galaxy or the observable universe, would be of an intelligent communicating civilizations?
Well, the Drake equation is just a wonderful way to organize our ignorance. Mm-hmm. You really can't calculate anything with it because there's so much uncertainty. But certainly over the decades since we last spoke, extrasolar planets, exoplanets, and extremophiles, different forms of life on Earth that we have discovered living in environments we once thought totally inhospitable. Those have been game changers. And indeed, once you begin to talk about all of this potentially habitable real estate out there and start thinking about ways to perhaps discover which of them are actually inhabited, then it makes it much more reasonable to ask the question about whether there's any evidence of technological civilization in any of these locations. So indeed, SETI is a term we've used since 1960, but we're now beginning to talk more about looking for technosignatures, which is anticipating these wonderful new telescopes that are going to be coming online, orbiting in space or ground-based, to do astronomy writ large, and wondering what we might actually detect when we begin using those telescopes. There's this.
How does technosignatures differ or narrow the original SETI mission to look for non-random signals?
Well, technosignatures is in fact a broader term because we're envisioning, for example, using some of these new telescopes, which will eventually allow us to actually get images of these distant exoplanets. Oh. And to open our minds and say, well, what might we find in such an image that would indicate a technological civilization? So not just signals in the optical and the radio and the infrared, but structures or planet husbandry that would be really strange. Suppose you found a planet, an exoplanet, that had no temperature gradient from the poles to the equator, because someone was in fact engineering that planet to be more of what they like to have in terms of climate and weather. Or there's this wonderful system called TRAPPIST-1, 7 approximately Earth-sized planets in orbit around a tiny red dwarf star, all very close to the star. Gee, when this system was discovered, it got displayed in the New York Times above the fold, front page, and there was an artist concept, and each of those planets looked different. But when we get a telescope that actually can make an image of all those planets, what if instead of being hotter on the shorter orbits and colder on the outside, what if all those planets looked exactly the same? Because they'd been engineered, right? They are being, and that's a technosignature, and it isn't a deliberate signal in any frequency, but it might be something that indicates a civilization with a lot of energy at their disposal and a lot of technological capability. So that's the kind of idea we're talking about with technosignatures. At the same time, we're continuing to make the radio searches and the optical searches and the infrared for signals.
Is it technologically feasible for a signal not to be a deliberate one that is highly focused? Is the resolution sufficiently strong that you could pick up a signal that is not deliberately being sent?
Yes, that's called leakage radiation. And if the transmitter is strong enough and it's close enough, we might be able to detect it. You can think about the early warning radar system that we had since the Cold War. Those transmitters are aimed at the poles, but in fact, that transmission leaves Earth and would be detectable by someone with a big enough telescope and a sensitive enough receiver.
The community has been thinking about what happens if there is a signal, and there are different kinds of reactions to it. Some are highly controversial and polarized. Some people say we should hide ourselves because if life on Earth is anything to be as an example as life in the universe, it is competitive, and we don't want to betray our presence for alien consideration. And so we have these others. SETI is, of course, very famous, Search for Extraterrestrial Intelligence, but how about METI and the messaging and communicating? What are those systems and what are those communities like?
They're a bit controversial. There's some people that say, you know, when you're in the jungle, you don't shout because the tigers will come and eat you up. Other people who say we're leaking radiation anyway, that horse has already left the barn, we're detectable from our own technology. And I think for me, the thing that makes METI a bit, and that's messaging to extraterrestrial intelligence, the thing that makes that a bit unreasonable from my point of view is that we're just too young and we're not grown up enough. We can maybe get completion on a 1-year plan or a 2-year plan. Maybe extremely rarely we can actually complete a 5-year plan. But if your strategy for success is that you're going to send a signal that will indicate to someone that you're here, you need to be thinking about a 10,000-year plan, right? Because if you transmit for a finite amount of time, that signal is going to go past your intended target in that finite amount of time. And if they're not looking at you in just the right way at just that moment, it won't be successful. So I think transmission is a really long-term commitment and strategy. And, you know, I think we are just not up to that task yet. I think as a young emerging technology, we should listen first. And then when we can get our act together, then we could transmit.
But your argument is more resource and efficiency related rather than this psychosocial analysis of what aliens may think about.
Right. Yeah, and in fact, if we ever detect a signal, statistically, it's going to be from a civilization that's a great deal older than we are. Anybody younger than we are really doesn't have the technology to be very detectable. So statistically, they're going to be older than we are. And from my point of view, I don't understand how you get to be an old technological civilization unless you outgrow all of the competitive and nasty behavior that perhaps helped us to get intelligent in the first place. So I think that simply because the civilization has made it to old age inclines me to think that they will have figured out a way to outgrow and discard all of the belligerent and difficult technologies that they started with.
That sounds very nice and optimistic. And it may be well the case in a large percentage of those civilizations. The problem is that it's a highly skewed and risk averse, that if there's one or just a very few on the other side, it can be far less than 1%. But those are the ones that you have to worry about. You have to worry about the outliers. So it's not just what should happen or what might happen statistically. It's worrying about the extreme tail.
Yeah, well, you need to go reread your Steven Pinker, right? Better angels of ourselves. Yeah, it is a point of view. I kind of would imagine, right, that in terms of longevity, the number of civilizations out there is a bimodal distribution. I have a lot of young civilizations, and some of them manage to get to old age. And so the older ones are the ones who I think will have, through cultural evolution, outgrown the pugnacious tendencies of their youth. The younger ones, many of them won't make it through, and maybe some of those are a threat to us. We'll have to see. I mean, I don't think that anyone is going to tolerate shutting us down as a planet in terms of electromagnetic radiation.
Yeah,
There are too many ways that we use those technologies. And so we are leaking, we are detectable. And if there's someone young and aggressive close by, we'll have to see what the future brings. I mean, people talk about the future singularity, the thing that will end all of us. And that might be it. But I think that I'm too much of an optimist, right? I wouldn't have been in this business if I weren't. So I'm looking forward to learning from some of those older technologies about how they managed to make it through this technological adolescence, which is so fraught with challenges. I'm just looking, and we live in the Berkeley Hills, and I'm just looking out, and there's a cat on my deck, which has, I don't know how it got there. Very pretty cat.
With the large number of exoplanets now estimated at virtually the same number of stars in the observable 10 to the 22nd, or whatever the huge number is, could I make that argument? You've made the argument that that increases our likelihood. Could I make the opposite argument and said that increases the Fermi Paradox, that we haven't seen anything? Is that a legitimate counter argument to what you're saying?
I don't think so, because I still, when you calculate how much search space there is out there in the cosmos and how much we've done, right? The last time we talked, I said if that search space volume was equal to the volume of all the oceans on the planet, that we've searched one glass. So I don't think it's much of a counter argument to say that we haven't found anything, because we've hardly begun to look. And now that glass, some students recalculated last year, it's more like a small hot tub worth of search space. So there's still a whole lot of exploration to do. And I don't think that we draw the really serious conclusion that we're the only intelligence in the universe until we have done a lot more searching.
So what does that mean until? So what is if you look at human civilization, what is your end date? I think last time we spoke, we both agreed that there is no answer to this question that is not awesome and extraordinary. You know, we're not alone or we are alone. I mean, those are the only two bimodal choices, and each one is awesome and riveting. But if you're looking at the whole history of humanity in retrospect, as it were, when would you think that you would be forced to make a conclusion that maybe we are alone, at least as a technological civilization? How long in the future would it take? given the rate of advances that we're doing in our in technosignatures and radio telescopes and the like?
Well, given the fact that communication or information about an extraterrestrial technological civilization could result by use of a technology that we haven't yet invented.
Sure.
Right? I don't see the end date anytime soon. I think the answer is going to be a practical one. When we can't raise funds from governments or individuals to keep going. And it's just going to be a question of whether we can continue this scientific exploration with someone's funds.
Yeah, I'm actually going beyond that. I'm giving the assumption that you have unlimited funds for all the rational things that you'll want to do. How many years in the future with a null result will you tolerate? And I'm using you as a personification of humanity in general. How long would that take? Is it 10,000 years? Is it 1,000,000 years? What is that date? Order of magnitude.
Yeah, I think it's more like 1,000 years.
Okay.
I think given the exponential improvement in our technologies and our ability to search, that in the next millennium or the next 1,000 years, we will have sufficiently explored a very large range of possibilities. And finding any technosignatures, will really be forced to say, okay, we're it, at least in practical terms. And we better do a heck of a lot better job at taking care of this planet than we've done in the past.
The relationship of time periods always kind of bothers me in a sense that what we're talking about is technological capabilities that humans have had in what is it now, 300-400 years of scientific history, and a few tens of thousands of years of what we call modern human history. And that's such a small percentage of the 13.8 billion years or whatever the current number is in the estimate, the size of the universe. There seems to be a disconnect between those two kinds of numbers.
Absolutely. And Phil Morrison had a wonderful way of phrasing this. He said that SETI is the archaeology of the future.
That's good.
And it's archaeology because of the finite speed of light. Any signal that is detected will have traveled perhaps 100,000 years to get here if it's within the Milky Way galaxy, if that's where it started out. But it's about the future because unless, on average, technological civilizations manage to exist for very long times, and not just in human terms, but in cosmic terms, then there will never be any two technological civilizations close enough in space to detect one another and coeval in time to overlap. So the fact of detecting a signal, Phil Morrison reminds us, would tell us that it is possible to have a long future.
No, that makes good sense. What about the argument with so-called Van Neumann probes that, given a period of 1,000,000 years, something like that, that you could have probes, non-life probes, artificial intelligence that could go to one planet after another and have an exponential increase in their reach, and so that you only need one civilization in the galaxy to reach that point. You would be able to see some obvious signatures every place, because 1,000,000 years, which is an enormous amount of time of exponential growth in technology, is still such a very small percentage of the time that stars and planets have been in existence.
That's right. And it's really hard to predict what that technology is going to look like. But we have some mysteries on the skies that we are currently exploring and don't have a very good answer for. There are such there's such a thing called the Kordylewski clouds, right? There are Lagrange points in the Earth-Sun system, which are gravitationally more stable for putting something that you would want to last for a long time. Now, these clouds are controversial. Some people can see them, some people fail to find them. But there's been a suggestion that those clouds might actually be made of little diamondoid nanobots, right? And someday, if they turn out to be a reality and we can get the opportunity to explore and investigate what the content of these clouds are, we may be surprised that it is in fact someone else's nanobots boldly going between star systems. There are also fast radio bursts, right? There are approximately 10,000 of these radio phenomena that go off every day, and they only last a millisecond or two. And it's only been the last decade that we've known about them, even though there are so many of them going off on the sky every day. We don't have a good, that is, an explanation for these phenomena, which are very energetic, that everyone agrees on. There's a bunch of controversy. But when I first saw that frequency time dynamic spectrum of a fast radio burst, I thought, we could do that with technology. We could, in fact, create such a strange signal, and it's not so far-fetched an explanation. In fact, it might be a more palatable explanation than postulating that these things are natural events coming from extragalactic distances, and therefore being so necessarily so hugely energetic. You know, maybe having an extraterrestrial technology create that closer to home is a viable explanation. Now, very, very few of my colleagues would indeed even conceive of that kind of an explanation, and they're certainly looking at magnetars and other natural phenomena as being an explanation.
But that's a wonderful thing to do, even if the odds are 1 in 10,000 that that's
Sure.
correct. When we're working on something like this, to explore, to push boundaries is exceedingly important. For example, when that asteroid came through the solar system, that I can't pronounce the name. How do you pronounce it?
Oumuamua.
Oumuamua. Okay, when Oumuamua came through, some individuals, Avi Loeb at Harvard, who's a good, closer to truth, a friend, speculated that it could be extraterrestrial. And of course, he was criticized significantly for that, and the data really didn't support it. But that's a good thing to do. It forces us to think beyond the tradition. So I might criticize it, but I love it.
Yeah, well, you know, all of us who read Rendezvous with Brahma while we were growing up, we thought the same thing. And of course, we use the Allen telescope array to observe that piece of extrasolar, apparently rock, and obvious calculations about how many of those there might be is also startling. There just could be a huge number of them that we have never seen. And learning how you get that kind of extreme shape, you know, the length to width ratio on that was enormously.
Right, a big cigar.
Yeah, how does that, what kinds of processes in the interstellar medium change something that was a fragment that's more likely to be spherical under self-gravity into such a shape? Lots to learn out there. Lots, you know, we just don't yet know everything. We should remain humble.
Jill, as we look at all these questions of humanity's place in the cosmos, in light of our current news, where if you look at borders between countries, virtually all over the world, there are substantial arguments and people losing their lives over rocks on the ground or in the water. and great threats to our civilization. What kind of perspective can you offer through SETI and through this whole way of thinking that humanity can really reassess its obsession with borders and rocks?
And skin color and all of this. Again, it's the cosmic perspective. It is that when compared to something that is not of this planet, that has not co-evolved with this planet, they will be so strange that by comparison, the differences among us are trivial. So it's Caleb Scharf, who's the chairman of the astrobiology department at Columbia University, has a really nice way of putting that. And in talking about the challenges that we face going forward, he says that a cosmic perspective is not a luxury, it is a necessity, that we have to figure out a way to solve all of these existential threats that life, humanity, and life on this planet actually face, and figure out a way to do it globally.
My last question, Jill, is really an unfair one, so I'm warning you in advance. You know, assuming you and I have another, I don't know, I'll be optimistic, maybe another 40 years of life ahead of us. What's the odds that we'll have either a technosignal or a non-random electromagnetic signal that we will all feel confident in? Give me the percent between 0 and 100.
It's somewhere between 0 and 100.
Okay.
And I think the only correct or only reasonable answer to that question is the last sentence of the Morrison and Cocconi paper from 1959. And that sentence is, the probability of success is difficult to estimate, but if we never search, the chance is 0. So I think just keep searching and thinking about new technologies as they get to maturity for whatever reasons. Think about how we could use them possibly to expand this scientific exploration and trying to figure out what our actual place in the cosmos is.
Let's take another data check in less than 10 years this time. So I look forward to our next conversation, Jill. It's always a pleasure.
Yeah, I'm really excited about the possibility that the answers to some of your questions might be different a decade from now.